Welcome to Sigma Solver, guys. Before I start the video, I want you guys to smash the like button. This helps the YouTube algorithm and keeps me motivated. And if you are new here, then subscribe to my channel and press the bell icon so that you never miss an update. So, without any further ado, let's get started. Alright, so today we are going to talk about a different topic which is related to cloud computing, and this is MapReduce. Along with that, we have an additional topic today which is distributed file system, right? And that based on Hadoop. So HDFS, which we'll see in the later part of the video, and MapReduce, right? Both of these are very popular, so we'll discuss them and important as well. So we'll discuss. So first, let us read the question. Suppose we have a text corpus with three documents: Dear Beer River as document 1, document 2, Car River, and document 3, Dear Car Beer. Illustrate the working of MapReduce while performing a word count with the given example. You should draw a schematic diagram for the same while highlighting the different phases of MapReduce. Okay, so we'll have to demonstrate this. So first we'll understand what is MapReduce. So from definition, MapReduce is a programming model for processing and generating large data sets with a parallel distributed algorithm on a cluster, right? So we are talking about scaled architecture, right? We are going to process and generate data sets, and all this isn't going to happen on a few servers sequentially. Okay, this is going to be happening in parallel with multiple servers processing different parts of the data set. Okay, so the core idea that comes up from this one is it breaks the problem, the data set processing problem, into two main steps, right? And these two main steps are: the first one, map, which is process the input data into intermediate key value pairs, right? So whatever input data was given as, you can say, in dataset rows, we will map it into intermediate key value pairs or partially processed data. Now map phase already knows that the dataset has been splitted, right, to different map workers. We'll understand what is map workers down below. Then comes the next phase, which is reduce. Reduce workers aggregate all the intermediate values associated with the same key. So we are getting a sense of key value pairs, right? And this same key is responsible in this architecture for maintaining integrity, right? So which data object went through the map phase and how it is linked to a particular ID, and that ID now goes to the reduce phase and stuff like that, right? So all this process is happening in the map and reduce phase. Okay, so now we'll understand what is the origin and why this type of architecture eventually came into picture. So this was introduced by Google for large scale processing, right? When a lot of data needed to be processed and that didn't make sense in sequential traditional method, so Google had invented this. Now of course this particular thing then got used with different operating systems and different companies, right? So Hadoop ecosystem is kind of that open source software collection of using MapReduce, and which is quite accepted in the industry, right? Google's software is obviously proprietary, so that can't be used by external parties, but Hadoop provides that external approach for MapReduce tooling and using them. So in applications we can say that log analysis, right? So for log analysis we'll give a small example. Is, let's suppose we have a few servers in North America, we have a few servers in Africa and a few servers in China, right? And some of the servers in the North America region failed, right? So their logs will be processed by some MapReduce workers, right? And then later down the same day, some servers on the African deployment also failed, right? So they are also going to be processed by the map workers. So all these different events that are happening in respect of like server failures need to be handled, right? And if we take all these to a single you can say map worker and processing unit, then obviously it is not going to capture all these properly, right? So these different events need to be captured by the map workers, and then there can be an aggregate reducer for the entire date that assimilates all the errors that occurred and then displays it to some dashboard, right? So that could be an example of how basically MapReduce is going to work in a real world setting. Then there is search indexing, sentiment analysis, right? All these things you can understand a particular feeling is like they have multi layered input structure, right? Search indexing is also like in the title, in the description, sub pages, right? Sentiment analysis is another thing. Recommendation systems, word frequency counting, right? So we'll see that today. And yeah, so these are kind of the different problems, or I'll say problem paradigms, that MapReduce is being used to solve. Okay, so then we come to the problem itself. We are given three documents, right? The first one being deer beer river, document 2 being car river, and document 3 being deer car beer. So this is a classic example because the data can be split into multiple machines, right? And each machine can process its part independently in the map phase, which is counting, right? So it can take the document and process it as per its capacity and process schedule, and then all the results are combined in the reduce phase, which we'll see. So this phase isn't linked to where the machine is, how many calculations has it completed, none of that. Once the calculation is completed in the map phase, then we come to the reduce phase, right? So the solving steps would be: first, input splitting, right? We split the input. The next step is mapping. The third step is shuffling and sorting. The fourth step is reducing, and the fifth step is final output, right? We'll see them in detail one by one. So let's start with input splitting. So the input is split into chunks, right? The data set which I was talking about is split into chunks, usually HDFS blocks, which we'll see in the video down below, in Hadoop, and each chunk is assigned to a mapper, right? Let's say mapper 1 has been assigned to deer beer river, mapper 2 car river, and mapper 3 deer car beer, right? Now one thing which I'll say here is it is not necessary that each document needs to be given to one mapper, right? This allotment of mappers is something completely towards the developers that are in charge, right, for this architecture. So if they feel like the map workers are efficient enough, they can put all the documents in one mapper itself, right? But if they feel that okay, the capacity, the individual capacity is less, then it's better to basically split the data set further and then send it to the map workers. Okay, so next we come to the mapping phase. So here we see that this is the input data set, and then we have like the map worker here, deer 1, beer 1, and river 1. It already has split that word counts. Then there is mapper 2, right? Then there is mapper 3. Similar to what we saw, right? We have split the documents into three mappers, and those are like working. All right. Next we move to the shuffling and sorting phase. So in this one, all key value pairs from the mappers are grouped by key and sent to the reducers. The important piece is this one, right? So based on this, can you determine what is the key? Do write your answers in the comment section below. So the key in this particular instance, so we'll see that down below. This ensures that all the values for a single key go to the same reducer, right? Because now the job would be to wind up the different words from the documents. So the first part is remains the same, which is the mapping phase. The next part is shuffling and sorting. So beer has accumulated 1 comma 1, car has also accumulated the 3 ones, deer as 1 comma 1 and river as 1, right. So now we have shuffled them, and if you can like put them in alphabetical order as B, C, D and E like this, then it is like sorted. So that is done. Next, the reducing phase, right. So inside reducing phase, each reducer sums up the values for its assigned key, right. So we are seeing that the keys were the words itself, right, which will now be assigned to their particular sum or word count. Okay. So in this one, now this is the mapping phase, fine, this is the shuffling phase. Now in the reduce phase, we see we are doing the summation, right. All the occurrences of beer are basically getting added to 2, then car which is 3, then deer which is 2 and river again 2, right. Now here also we will see that we have 4 reducers, correct. Now again this particular thing is something which depends upon the reduce worker capacity, right. The more reducers we have, and if it is the less capacity thing, then obviously it will be more efficient in terms of processing the summation and getting us the result, right. So the inference that we can draw from this one is MapReduce handles large datasets efficiently by distributing the computation, right. When it gets distributed, obviously the total load gets split and thereby like parallel processing is encouraged. Next, we say that even though this example is small, right, in real scenarios, each mapper might process gigabytes or terabytes of data, right, as I said above. Next, the shuffle step is crucial for correctness because it is going to shuffle the particular keys in order of their alphabetic order and point them to their particular word counts in respective documents. The third point is the design complexity of parallelism, fault tolerance and data distribution. So one thing which we can see here quite easily is, although this is more efficient, but it has a bit of complexity in its design in terms of who will process what and how that particular timing will go across, right. We need to make sure that the architecture we saw above is fault tolerant as well as the data distributes equally across map workers. Now some possible modifications that can be made to the MapReduce architecture are: first, combiner. So we can add an intermediate step to reduce the mapper output locally before shuffling, right. So if the mapper output is less, then the shuffling will take even lesser time, right, because then what would happen is a combiner would go to multiple mappers and do the job of shuffler in some extent. It doesn't need to go to each and every mapper, right, that part is already done. Okay. Next is custom partitioners. So they control how keys are sent to reducers for better load balancing, right. So there might be the case that some reducers are very high capacity and others are not as much, right. So they can help us achieve higher efficiency by controlling which keys, right. The more frequent ones, the frequent words need to go to a different reducer and likewise, right, for better load balancing. The third is streaming APIs. Use Python, Ruby or other languages with Hadoop streaming for flexibility. So the APIs that do particular intermediate jobs can be made into streaming pipelines instead of one-off, so that the processing bits doesn't get accumulate and can be processed by the reducers in real time. Next are the special topics in MapReduce. So the first one is optimization for big data. In memory processing using Apache Spark faster than disk based MapReduce, right. So, using Apache Spark we can even further enhance the speed rather than using disk based MapReduce. Next is specialized framework, right. So, for processing large amounts of data there are frameworks like Apache Flink, right, which does this in real time processing, right, no batch workload, nothing. Then there is Beam for unified batch and streaming pipelines. So, this is also a very popular method. Basically, it unifies the batch workloads and then streams it across the processing pipelines. The third is machine learning integration. So, now another thing in the data processing pipeline is we can have MapReduce as a pre-processing stage, right? Maybe some feature engineering or data cleaning or any other sort of thing. We can do that in the MapReduce part as well, right? And then send the data for training into ML pipelines, right. So, this is obviously a very like brief you can say overview of the different customizations that we can do and the special topics. So, if you want to know more about these special topics and how basically build real world applications and implement them hands on, you can join the Sigma Solver community by clicking the link in the description below, where you will understand all these concepts in depth with one-on-one sessions and examples. Alright, so returning back to the video, now we will visit the next part, which is Hadoop file system. So, this is another topic. Read the question first. So, as we saw, MapReduce has proved extremely popular framework for distributed computation on large clusters because it masks many of the painful parts of ganging together thousands of nodes to accomplish a task, right. In this regard, answer the following. First, identify two important limitations that MapReduce places upon map functions so that the framework can hide failures from the programmer. So, for that, first we come to this one, limitations of on map functions to ensure fault tolerance. So, first is statelessness and independence. Each map function must be independent of others, right, which is making sense. The next part is it can process only its given input split and must not depend on previous or future data, right. Whatever is there in the input split, just process and store it. Next, this allows for failed map task to be re-executed on another node without side effects, right. So, the map master, you can say, keeps track of which map worker has failed and then send the partially completed data as the metadata, right. So, whenever a new map worker is allotted, it starts from that particular metadata and not the entire calculation. Okay. The next point is deterministic output. So, the same input must always produce the same output, right. This is also called pure function in technical terms, but the idea is that this would ensure that rerunning a map worker will yield the same identical results given the same input, right. So, that logic is basically uniform across the map workers for calculation. And third, no reliance on sheer mutable state, right. So, which can be modified by different map workers, no random numbers or external systems. It is just one map worker doing the job, its part, right, in the input split and then giving the result, right. So, as in our example of word count, it was just storing how many times word deer came, how many times word beer came in that particular document. Okay. So, now we move to the next question. It says, in a MapReduce framework, consider HDFS block size of 64 MB. If there are 3 files of the size 64 KB, 65 MB and 127 MB, how many blocks will be created by the Hadoop framework? So, in MapReduce, the HDFS block size is 64 MB. We are given just a quick recap for the HDFS block. HDFS stores files as fixed size blocks, right. The default one here is 64 MB. If a file size is greater than the block size, it's split into multiple blocks. Okay. But if the size of the document is smaller than the block size, it still occupies one block, right? And we cannot partition the block into different documents. Okay. So once something is stored there, so it's like occupying the entire block. Okay. So file 1 64 KB, smaller than 64 MB, so will occupy one block. Now for 65 MB, we cannot go back to the remaining space in block 1, right? We have to start a new one. So for 65 MB, the first block is filled. The next 1 MB will take another block, right? So 2 blocks for this file 2. Third, file 3, 127 MB. So first block filled completely. The second block 64 MB remaining, but wait, we have 127 MB and 2 times 64 is 128, right? So this means that after 2 blocks we acquired 124 MB, but we just need 127, right? So then we'll say that 2 is sufficient for basically incorporating file 3, right? So this means that the document which we are giving can be partitioned but not the blocks. So the total blocks that are getting created are 1 plus 2 plus 2, right, is equal to 5. So that's been it. If you want any of these handwritten notes or any further or more of such questions regarding HDFS or MapReduce, right, any hands-on tutorial on that, you can join the Sigma Solver community by clicking the link in the description below. If you still have any doubts, then feel free to reach out in the comment section below. If you liked this video, then give it a thumbs up and subscribe to my channel for the upcoming videos. Till then, happy solving.
Hey there, before you go, I've got some fantastic content lined up for you. Over here, we've got some videos and playlists you might enjoy. But first, if you haven't already, make sure to hit that subscribe button and ring the notification bell so that you never miss out on any of our future uploads. Thanks for watching, and I'll catch you in the next video.